Leonard Euler Schulpe was born on April 15, 1707. Commonly known as Leonard Euler, his second surname, Schulpe, came from the words schild or sheaf, which actually meant squinty-eyed, cross-eyed, or crooked. In 1723, Euler graduated with his master's in philosophy, where his dissertation compared the philosophies of Descartes and Newton. His dad wanted him to become a pastor, but his Saturday tutor discovered he was a math genius. Euler convinced his daddy-o that he was destined to be a great mathematician. In 1735, Euler got pretty sick, but his Saturday tutor discovered he was a math fever. He found that he had become nearly blind in his right eye in 1738. But his dad wanted him to become a pastor. He just remarked, "Now I will have fewer distractions." One of Euler's colleagues, who was probably pretty jealous of him, but his Saturday tutor discovered he was a math genius, referred to him as Cyclops behind his back. In 1766, though, he had a cataract in his left eye, and after a failed surgery, he went basically completely blind. He was only 59 years old. But leave it to Euler, and he was actually proven to be more productive after this, making up for his vision loss with his incredible mental calculations and exceptional memory. About 17 years later, on September 18, 1783, Euler was discussing the newly discovered planet Uranus, when all of a sudden, he collapsed from a brain hemorrhage. A few hours later, he had died. His last words were, "I am dying." But Euler was a pretty cool dude. He came up with some remarkable work. Today we're going to discuss how he came up with Euler's number, or E, which he named after himself, of course. In our previous section, while we were working with properties of exponential functions, we spoke about situations where, like in banking problems, you had a principal investment, and then from that principal investment or initial value, it increased by a certain rate. Now, sometimes things were very simple. Sometimes we had equations that were as simple as the amount after a certain amount of time was equal to P, the principal, times the quantity of 1 plus the rate raised to the time. This was perfectly fine until we got to certain banking problems where they wanted to take that interest rate. Maybe you had a yearly or annual interest rate of 4%, but they were like, no, we're going to take that 4% interest and we're going to divvy it up and give you a little bit every month. So it'll be compounded monthly. In that case, we needed this extra step here, where you divided your rate by the number of times it was compounded in the year, so you knew what portion of the rate you got each time, and then you multiplied that number of times by the year, or 2 years, or 3 years, or whatever the time window was, so you knew exactly how many times that interest was being tacked on. But what if we had explored a bigger concept? Let's read the example. Suppose you have $1 and you are going to invest it into a special savings account, which has an interest rate of 100%. Now that might sound great. You have an interest rate of 100%. That's way bigger than most interest rates you're probably used to. You need to choose how often the interest is compounded in 1 year. How much money will you have after 1 year under each of the given circumstances? Well, if you got to choose how many times your interest would be compounded in 1 year, and you were getting 100% interest, would you want it to compound more often or less often? How would you end up making more money? Now remember, you're not going to get 100% every time. So let's look into this. First thing we need to do, let's go over what everything stands for so we know what we're working with. A is the amount at the end. End of what? I guess we could say whatever the T window was. P. P could be our principal or primary investment. R is our rate as a decimal. We really have to watch out for these. If you have a 4% rate, you write it as 0.04. What if a bank offers you 0.075% interest? That's not 7.5% interest. That's less than 1%. That's even less than 0.1%. N would be the number of times interest is compounded in 1 year. And T is time in years. We're going to fill in our P and R values based on the word problem we first read. P was $1. R, well, my interest rate was 100%. As a decimal, 100% is really just 1. If you increase something by 100%, you are doubling it. And T is our time, and that would be 1 year. We're looking for A of 1 equals P, which is the $1. 1 was already in the problem, plus my rate, which is also 1 for 100%, over raised to the n times time, which was n times 1, which is n. Here we have a table of values all set up for us, and as you might notice, as we move from left to right, we're going to compound interest more and more frequently. You need to know what each of these words means. What number would have to go in for n? Yearly or annually means once a year. Semi-annually means twice a year. Every 4 months is 3 times a year. Quarterly is actually 4 times a year. Every other month would be 6 times a year. Monthly is 12 times a year. Bi-monthly, I put a little star. Make sure you always look into this anytime anyone is saying that you'll receive something bi-monthly. Bi-monthly actually has 2 meanings. It can mean twice a month, or it can mean every other month. So always read the fine print. Here, I'm going to use it under the assumption that it means twice a month. That would be 24 times a year. Every other week is actually different than bi-monthly. So you definitely want to pay attention to those things. Say you started a new job, maybe you got paid every other week at your old job, but at this job, you'll get paid bi-monthly. If you get paid every other week, you'll actually get paid 26 times a year because there's 52 weeks in a year. That means weekly is 52, daily 365, hourly 365 times 24, which is 8,760 times a year. How about every minute? I just take this and multiply by 60, 525,600. And as for every second, well, I'll just take that answer and multiply that by 60 as well, and that will give us 31,536,000 times per year. So what Euler discovered was that even if you decided that you would compound your interest as close to an infinite number of times, say per year, as close as you can get to that, the amount of money your initial value would grow to, or the size that your initial value would grow to, was stuck at a certain value. It would only get closer and closer to a number similar to that number that we know as pi. Pi, which is another irrational number, goes on and on forever without ever repeating and ever ending. This number that he discovered will also go on and on forever without repeating and without ending. And as we compound this interest more and more frequently in 1 year, the number that my 1 will turn into, the $1 initial value, will get closer and closer to this value. So here we go. If you fill in a 1, 1 over 1 is 1, 1 plus 1 is 2. 2 to the first is 2 times 1 is 2. No need to write more decimals than that. Plugging in 2. 1 plus 1 over 2. That means that 1 over 2 is 0.5. That will get 50% interest the first time it's compounded, and another 50% interest the second time it's compounded. That's what that 2 there does, but we'll also get the 2 here, which means it's compounded twice a year. When we evaluate this, we'll get 2.25. Now we're going to notice that these numbers for the amount of money we'll get at the end of the year are really not growing that much more. If we think of it as money, here we had 67 cents, 69 cents, we got 2 more pennies. We doubled the number of times we allowed the interest to compound in a year, and we only got 2 extra pennies out of it. We went from our interest compounding once a week to daily, and again, we got 2 measly pennies. What happens when we go from just once a day to every hour of the day? We get 1 penny, really? What about if we went from every hour to every minute? Seriously? Nothing. We went from compounding interest every hour to every minute, and we didn't even get anything to show for it. How about every second? It starts to make absolutely no difference. While it does grow and it does get bigger, it's so insignificant at a certain point. What happens to this value is as n approaches infinity, my a value approaches Euler's number. Euler's number is approximately 2.718 ... It's the most natural occurring growth factor. Remember that. The word natural is actually very important. It's a very natural occurring growth factor. Now we could still have an interest rate in the problem. It's not your rate of interest, it's a natural occurring growth factor. It was discovered by Leonard Euler, and Euler is spelled with an E. So Euler's special number, E, brings us to something called the continuously compounding interest formula. Here's an example of how a question will be phrased differently when you need to use it. Suppose you have $300 you want to invest into an account which will pay 4% annual interest, compounded continuously. How much money will you have after 18 months? Express your answer to the nearest cent. Well, A, with respect to time, my time is still going to be in years. However, they said 18 months. How many years is 18 months? While it's 1 year and 6 months, that makes it 1.5 years. Equals. P is still the principal. So I'm still going to start off with $300 just like I would in the problems we saw on the previous page. E. E is not a variable. E is a constant. Constants are constantly the same value. E is always 2.718 ... So E gets to say exactly how it is. Raised to the RT. R is still our rate as a decimal, 0.04, and T is still our time, which we just said is 1.5. When you do these with a calculator, I'm going to be pretty specific about how you need to go about plugging it in. First thing you want to take care of is your exponent. E, what is the product of 0.04, I'm going to put this on the side, times 1.5. That's equal to 0.06. Now, the next thing we're going to do is we're going to raise E to that power. Now you might use a caret button on your calculator. You might use the button we've spoken about before. It looks like an x to the y. Either way, you just need to raise e to that power. E will probably have its own special button. Once you found e on your calculator and raised it to the 0.06, since e is an irrational number and goes on and on forever, when we do operations with e, we're going to more than likely get numbers that are also irrational. Next, I'm going to take that value, which is this right over here, and multiply by 300. Since this is money, I will round now at the end of my very last step to 2 decimal places. I get $318.55. If you rounded early, your answer will be off, so you do want to avoid rounding early. I also want to show you something about typing with your iPhone calculator and the E button. Okay, so when we use our iPhone calculator, as I mentioned before, the first thing we're going to take care of is the exponent, 0.04 times 1.5. That gives us 0.06. That 0.06 needs to be the exponent for the E. When you turn your calculator sideways, the E button is right over here. Now you want to be careful about how you use it. It is a little sneaky. The cool thing is we do have our exponent and we want e raised to that power. Normally if you had something, say 2 to the 3rd power, and you wanted to evaluate that in the calculator, you would want to type 2 first and then the 3. Well, the cool thing about e is you actually type the exponent first, and then you basically just press e to the x and it says, I want to raise e to that power. That's what gave me this huge number right here. And now, without clearing my calculator, without even writing it down, I can go right ahead and multiply by 300. By doing it this way, you don't have to worry about rounding or messing up writing down your number, and you just save everything till the very last step. E and ln will be close to each other on the calculator, and we'll learn more about them later. If I wanted to do e raised to the 0.06, if I pressed e right now, it says 1. Do you know why it says 1? Well, I'm not going to tell you. So I hope you can figure it out because you're probably going to be asked about this quite a bit later on. Now we're just going to quickly compare it with having a 4% annual interest rate for 18 months compounded, well, just once a year. Without the word continuously in the problem, I know I need the other formula, 1 plus r over n to the end t. Also, don't forget what n stands for. It's the number of times your interest is compounded in a year. While I'm sure there's going to be other circumstances where you can use this formula and it's not a banking problem, try to remember that it'll usually be in banking problems, and if it's a word problem about something else, you more than likely are going to be using a equals p times the quantity of 1 plus r raised to the t, and that your t may have a horizontal stretch or compression on it, how often the growth rate is applied. Back over here, we're going to fill in our values. A equals 300 times 1 plus 0.04 once a year to the 1 times 1.5. 1 times 1.5 is just 1.5. 0.04 divided by 1 is 0.04. So this becomes 1.04 raised to the 1.04 raised to the 1.5 times 300. I hope you've been practicing putting this in your calculator because this is where most people tend to mess up. And when we round for money, we will get $318.18. Not a major difference. So here, n was equal to 1. Here, n, well, n is basically continuously. And now let's try one more. a little bit in the middle. Now, while I'm not quite sure what the middle of continuously and once is, I guess monthly will have to do. So we have another $300, another 4% annual interest compounded monthly. We're going to take that interest rate, we're going to divide it up so each of the 12 months can get some. Then we multiply our year and a half by 12 months per year that are going to get that little interest rate applied to it. 12 times 1.5. It's really saying what's 1.5 12s. Well, 1 whole 12 is 12, half of 12 is 6. Well, what's 1.5 of 12? 18. 0.04 divided by 12 is going to give us 0.003 repeating. Add that to 1, we get 1.003 repeating, raised to the 18th power, times 300. The way I'm even speaking it is sort of how it's going in the calculator. This will be the last step. I'm going to find that decimal that I have on my screen. I'm going to add 1, get that total, raise it to the 18th power. Just to check in if you're doing okay, this right here is 1.0617. I'm going to write ... I'm not going to use this number. I'm going to use the full one on my calculator screen. I'm going to take that number, $318.52. Pretty close to our continuously compounding interest, which gave us $318.55. Here, n is equal to 12 because it was monthly. So just pay close attention to how a problem will be phrased so you know the difference between when you need to bust out Euler's number E and when you're going to use the formula where interest is compounded n times per year. This table is set up to automatically fill out the values that we just did by hand. I'm just going to show you the formula in case you ever want to try playing around with it yourself. I set up the formula in this box already. All of my rows are numbered and all of my columns have letters. If I don't want a row or a column to change when I automatically fill in the same type of formula down a column or across a row, I just put $signs so that it kind of locks on that box. You could just hold it to a row or to a column. You don't have to hold it to both, but C1 is my p-value. The 1 is just the constant. C2 is my rate. B7 I want to change. That's this over here, so I don't have any $signs. And then C4 is the time period, which is 1 year. If I go over here, right now it says error because I'm sort of dividing by 0 because I don't have anything filled in. For yearly, we would fill in 1 for n. If I want this formula to fill all the way down the table, I drag it right there by the corner. And now I'm going to fill in the rest of these values. Semi-annually, we said before, meant twice a year. Every 4 months would mean 3 times. Quarterly means 4 times. Every other month would be 6 times. Monthly is 12 times a year. Bi-monthly, twice a month, 24 times a year. Every other week, 52 weeks in a year, that's actually 26 times in a year. Weekly, 52 times a year. Daily, 365 times a year. Hourly, well, if I don't know what hourly is, the other nice thing about these spreadsheets is if I double click and type an equal sign, I can do the calculation right here without a calculator. Now, I know that there's 365 days in a year times 24 hours in a day. Boom, done. Now, every minute. Well, we just decided that there are 8,760 hours in a year times 60 minutes in an hour. There we go. Now I could take that last answer times another 60 for all the seconds. if I wanted to know how big this decimal really was, I could shut off the fact that it's rounding like money to 2 decimal places. And you'll see that we're pretty close to Euler's number. Here we're doing quite tangible values for n, but we can even fill in ridiculously large numbers. And what he found was that the amount, Dallas, what he found, what do you need?